My great pleasure to introduce our speaker today, Patrick Reichherzer, traveled far away from UK. Patrick is about a Benjamin Fellow at University of Oxford, and he did his undergrad in Germany and then a PhD jointly in Germany, Wu University, and in France, Paris University. And Patrick is an expert on cosmic ray transport, and he will tell us about the interaction between turbulence and the cosmic ray today.
Thanks a lot for the introduction. Indeed, I changed my topic slightly from focus on micromirrors that was announced to something more general about cosmic rays and galaxy clusters. So I will tell you how cosmic rays will travel through these beautiful galaxy clusters. So these are some simulation results, how they may look like in stellar column density and gas column density. And one aspect that's really important for that problem is that cosmic rays have a gigantic range of different energies. So here you see the spectrum of cosmic rays that we measure on Earth. And on the x-axis, you see a gigantic range of energies from below GeVs up to above EeVs. And in the spectrum, you see that beautiful power law that extends over a huge range of energies. And the question now is, how do these cosmic rays propagate through the universe, and in particular through galaxy clusters? And throughout my talk, I would like to complete the right figure, where on the y-axis you have the diffusion coefficient and on the x-axis the energy. And as a first step, I would like to motivate why the diffusion coefficient of cosmic rays is a good quantity to keep track of in order to understand how these cosmic rays travel through the universe. After that, I will then discuss the diffusion coefficient in different regimes, first at the highest energies, then at the lowest energies, and then in the range in between. If you look at that spectrum again, you may wonder, why do you have to treat cosmic rays in different regimes differently? Because it's a kind of beautiful power law, and naively you could say, okay, it's a charged particle, moves through magnetic fields. So why are there different regimes? You can kind of get a feeling when you look on the right side of these HD simulation results that cover also many different scales. So if you go from one image to the next one, you zoom in by a factor of 10. And in these simulation results, you see that there are many different structures on different scales. And cosmic rays, when you look at the large scales, will behave differently when they are in these more denser regions compared to outside, where also the magnetic field is a little bit weaker. So that already gives you kind of a hint that there should be different scales involved. And I will show you in my talk that there will be then also different interaction and mechanisms of cosmic rays with magnetic field on different scales, introducing interesting effects on the cosmic ray transport in general. So if you zoom in a little bit more and weight the y-axis with e to the power of 2.7 of the spectrum, you see that there are indeed some interesting features. So it's not a perfect power law. There are some interesting features at different energies. And here you see observations from many different observatories that all agree pretty well with some tiny tensions, but overall they all agree pretty well. And if you want to understand and learn something about cosmic ray transport, you want to, in addition to these observations, also conduct numerical simulations. And for numerical simulations, you have different regimes depending on the energy. So at the highest energies, on the right, you can basically treat your plasma, your magnetic fields as static, and then simply use test particle simulations to propagate your particles through your magnetized surrounding to understand the transport properties of that. If you go to lower energies, you cannot use that simple assumption that cosmic rays do not interact with the magnetic field. So you have to involve big simulations where you have a feedback of your charged particles onto the magnetized plasma. That's why you have different regimes, how you should treat the cosmic ray transport with different numerical approaches. Throughout the talk, I will focus more on the high energy regime. So I will only mention the test particle approach of cosmic rays to study the transport. And this here is a rough schematic of how cosmic rays behave in different regimes, different energy regimes. So in the weak magnetic field limit, or in the high energy regime, so these are interchangeable. So the really relevant quantity is the gyro radius with respect to the outer scale of your turbulence. So if your gyro radii of the cosmic rays are gigantic, then they will most likely only get small angle scattering deflections in your magnetic field. And these add up as a random walk and will, in the end, at really large scales, lead to a diffusive behavior. But the confinement is not really strong because we only have, after large steps, small scattering. If you go to the resonance scattering regime, RSR, over here, where the gyro radius becomes comparable now to your scales of your turbulence cascade, you have resonance scattering of cosmic rays with the magnetic field structures. And also particles can then easily follow individual field lines. And as field lines diffuse, your cosmic rays will also diffuse. And then going down to low energies, you also have particles being trapped in magnetic bottles. And going to even low energies, you come then to the regime where cosmic rays excite turbulence with the streaming instability, and then kind of generate also fluctuations at which other cosmic rays can scatter off. So putting that back into this kind of overview schematic, you can safely treat cosmic rays in the resonance scattering regime and the quasi-ballistic regime, and to some extent in the mirror regime, just using the test particle approach. So in these environments, you get all the relevant physics, given that you have a good description and like an MHD description of the magnetic field, treat it as a static one, and then you will have a sufficient numerical framework in just treating cosmic rays as test particles propagating through that field. And you will get all the relevant interaction processes that in the end will result in a diffusion coefficient that you can then numerically observe. Give you just a few examples of how some example trajectories may look like at different regimes. So if you use an magnetic field here, that's just a synthetic one with some background field pointing upwards and some turbulent magnetic field on top of it, and then solving the equation of motion and following the particle. It's initially mainly dominated by the background field with tiny deviations from a perfect spiral. And that's the initial ballistic propagation of a particle. After some time, you will notice that particles then, especially the gyro center, moves then randomly. And if you trace that particle and compute the diffusion coefficient of it, it will become diffusive. That's exactly what I showed here. I simply give the definition of the spatial diffusion coefficient that measures the spatial expansion of a particle as a function of time, and resolve the parallel component with respect to the background magnetic field, which is this one here, and the perpendicular component, which is this one, where you see the gyro motion, especially at the initial ballistic phase. And if you wait long enough, evolve the particle long enough, you will see that both components, the parallel component and the perpendicular component, will find or will result in a plateau, which means that you are in the steady state diffusive limit of your particle transport. And whenever I show you diffusion coefficients in the future, the diffusion coefficients are simply, after waiting a long time, the final converged values of your running diffusion coefficient.
What was the field here?
So that's a synthetic turbulent field with a background field along the z-axis and then simple summation over plane waves as a turbulent.
How big was delta V over B? Like when you say perpendicular diffusion W, what does that mean? You go very turbulent.
So here the background field is 10 times stronger than the turbulent field. So you have a really strong alignment of so when you go back to the field lines, they look something like that. So you have your basic field always points upwards with some tiny deviations due to the weak turbulence.
The Larmor radius must have been microscopic, right?
So the Larmor radius, it's larger than the fluctuations. That's true.
When you say some other plane waves, this is somehow band limited, so that you're not getting resonance scattering, or?
Yeah, so I think in that case, exactly. So if you do that, you only constrain yourself to a certain inertial range of your turbulence. So you specify the inertial range of the turbulence and only generate waves that are in that turbulence with a given prescribed spectrum.
In order to get diffusive behavior, I need to take waves that are
Resonant.
long, that are resonant or not.
And you get both. You get diffusive behavior when your Larmor radius is larger than your waves. But that's the small angle scattering limit. So then basically you have, we go back here. In that case, here on the right, your gyre radius is much larger than your typical or your maximum fluctuations in the turbulence. And then you can treat basically each turbulent cell. So the cell size is approximately the largest fluctuation size. And then you can basically treat each individual scatter event as a deflection, small angle deflection. And when they add up as a random walk, you still get diffusive behavior.
Right, but will that stop once you get into the resonant regime? The behavior will become different.
It will become
So
different.
you band limited it at some maximum K,
Yes,
so that doesn't, you don't get any of those resonance
exactly.
scatterings.
Yes. To further understand why diffusion coefficients are a relevant quantity, I'll show you here an example of cosmic ray confinement to galaxies, where you can write down the transport equation of cosmic rays, and in the most simple case, if you just care about transport, you neglect everything that's related to momentum diffusion, effective energy changes, or effect in general, and only care about spatial diffusion. So how do cosmic rays spatially evolve in such a setup? And treat the steady state case. So after a long time, your system will be in a steady state. And then the original transport equation shown here simplifies to something much simpler, especially if you then also assume that the escape term, which is this one here, simply describes the, well, it depends on your escape time of your cosmic rays, so it's inversely proportional to that. If you solve then your transport equation with all of these simplifications, you get that your cosmic ray density should be approximately the escape times, which could be energy dependent, times your sources of cosmic rays that also have a prescribed energy dependence. Then there are two cases. If you're in the simple case is the ballistic case, where your cosmic rays do not diffuse yet, then the escape time is simply given, if you still have relativistic particles, it's simply given by the system size. And if you're on the diffusive limit, the escape time is given by your diffusion coefficient. So simply when you have your diffusion coefficient definition, so the spatial displacement over time, then you see that you basically can change that equation to get an escape time that roughly approximates if you ask, okay, if you have a cosmic ray source at the center, if you have kind of a volume, then the cosmic rays have to escape the typical size in order to get out of your system, and then you simply have this dependence of your escape time on your diffusion coefficient.
So when you do this, you keep you use a proper model for the galactic number density, so it's actually declining exponentially in radius.
Exactly. Yeah, some people do that, exactly. So not in this example, so that's just a rough sketch of how you can do, but yeah, if you do it, then you keep track of the densities, but also of the magnetic fields, because magnetic fields also decrease magnetic field strength with increasing radii.
How do we know the induction term is important with winds carrying?
Yeah, exactly. In the center of typical galaxies, this approach is not really valid because then attraction should take over, especially at low energies.
And there are no loss terms here, like the energy loss and so on.
So the only loss term is this escape term here. So you basically assume that cosmic rays, once they travel this distance they are lost.
And the energy, there is no loss of energy.
So in that approach, I neglect everything that's related to radiation, synchrotron cooling, and so on. But you can include that, and you just can't simply write down an analytical solution to that. You have to then solve it in the end. Well, maybe in some certain limits you can write an analytical solution, but in general, if you include all of these effects, you typically solve it then numerically.
Just sounds like the total amount of energy in cosmic rays will be steadily growing because the source is not zero, right?
I mean, yeah, you have a source, but you also have escape term. So at some point you will have a steady state, and the solution here should describe the steady state after a long time. So there shouldn't be any significant increase. So the spectrum changes slightly. So the result of basically that leaky escape of cosmic rays, that's energy dependent because cosmic rays spend time in the galaxy depending on their energy, results in a change of your spectrum in the end. So this initial spectrum that you get at sources will steepen depending on your energy dependence. So that here just gives you an overview of numerical methods of how to propagate particles. The most simple one is just solving the equation of motion. And that's something I will that I've used whenever I show you plots in the future in the talk. But you can also use statistical approaches to model cosmic ray transport. But then you need, as you see here everywhere, the diffusion tensor. So in order to use these statistical approaches, which are much faster and more efficient, you need to understand how cosmic rays propagate in the first place. And then you can model radiation effects and so on. So first, you use equation of motion to understand how cosmic rays behave in general. You can compute diffusion coefficients. Once you have diffusion coefficients, you can use in the end more statistical approaches that are much faster. So that here is now the overview of like the zeroth part of my talk, why the diffusion coefficient is relevant. It's relevant, first of all, to use it for numerical simulations that are more complex, to have efficient simulations. Having a proper description of diffusion coefficients helps in modeling cosmic ray transport. But it also in general has implications on cosmic ray escape times. In the diffusive limit, it depends on the diffusion coefficient. So an energy dependence on that helps you understanding how long cosmic rays can be confined to certain astrophysical systems. And the spectrum is steepened if you have diffusive transport by alpha, and alpha is the energy dependence of your diffusion coefficient. So if kappa depends on alpha like that, you will steepen your spectrum in the most simple case of the leaky box approach. So now I will go through the different regimes and present you some numerical but also laboratory results on how diffusion coefficients of cosmic rays should look in different regimes.
You know, this is definitely a diffusive process. For instance, if you have field reversals,
So in most,
the gyrators.
yeah. So you don't have always diffusive processes, but I would say that diffusion dominate in many instances. But you have sometimes advection that dominates, like in the center of the galaxy, and certainly at other places. But nevertheless, you can, I mean, in the end, the goal is to use a more general transport equation, and then you feed into the diffusion coefficients and advection terms and so on, and then let the simulation run and see what happens. And then you will see that sometimes diffusion dominates, but not always. But nevertheless, you need a proper description of diffusion in the environment. So in galaxy clusters, the highest energetic cosmic rays have still gyro radii that are probably comparable to the system size and therefore larger than the typical scales of a turbulence, because the turbulence scale is a little bit smaller than your system size. So a really high energetic cosmic ray will undergo small angle scattering when traveling through a structure like that. So that's again a simulation result of galaxy clusters. And for cosmic rays, the really relevant quantity is magnetic field. At least at these high energies. Later I will show you that the temperature also matters for lower energetic cosmic rays. But for the highest energetic ones, only the magnetic field matters. At the highest energies, you can simplify your approach of understanding cosmic rays by just studying in detail what happens if you have one cosmic ray source and shoot particles through them. So that's basically the situation where you have somewhere a source, cosmic rays travel through the magnetized universe, and then you wonder what happens on the signature on Earth. How does it look like? If you increase your cosmic ray energy, the deflection will decrease, because at some point you are in the small angle scattering limit, and the higher you go with your energies, the smaller the deflection will become. And at the highest energies, you won't have any signature of the magnetic field anymore. So you can then illustrate that process a little bit by taking some sources, and I've used source positions from Starry Night from Van Gogh, just extracted them from the painting and run a simplistic simulation where I propagate then these cosmic rays through a magnetic field, and in the end check how these cosmic rays signatures would look like on Earth. So that's a highly simplistic model, but just to give you a basic understanding of the effects of the magnetic field and how we could observe them. So I think the interesting part, when you now compare different energies, so I've repeated that experiment for different energies, is that intuitively easy to understand that at highest energies, you will exactly get the signatures from where I've taken them from the painting. When you go to lower energies, especially at the lowest energies, you will see that you completely lose track of where cosmic rays originate from after going through magnetic fields, turbulent magnetic fields. And in reality, unfortunately, we are with almost all energies of cosmic rays in the left limit. So we lose completely track of where cosmic rays do come from and can't easily trace back if we observe a cosmic ray just solely based on the kind of angle and direction at which we observe it. We cannot say where the cosmic ray comes from. So this slide kind of summarizes a little bit the current situation where we have many potential cosmic ray sources. Some are more likely than others. But we, first of all, have still uncertainties in the different classes that can accelerate particles, and then also in individual objects. So there are many potential objects, but we can't really say which one is exactly responsible for cosmic rays that we observe here. So these are observations from Piaget collaboration. We cannot 100% say that these cosmic rays come from a certain galaxy. There are some correlations, but they're still not at 5 sigma level. So the difficulty is that there are so many uncertainties in both the transport, so also about in general how magnetic fields exactly look like and how cosmic rays then behave in these magnetic fields, but also about where these sources are exactly. Therefore, you can move to laboratory experiments where you try to mimic the complex situation in the universe by having an experiment in the laboratory that generates with high energy lasers and then kind of elaborated setup, generate a plasma that to some extent can mimic the plasma that you can find in the universe. So in that example, they if you scale the size of the plasma and the energy that they use as a proton beam, so they shoot charged particles, so proton beam with a certain energy through that plasma with something like 13 MeV cosmic ray energy. If you can kind of translate these values to large scales that you would have in the ICM, you will find that it's comparable to the really high energy limit. So your gyro radii of your protons is larger than your outer scale of the turbulence that you have here. And therefore you should expect the small angle scattering limit in that experiment. The nice thing about such an experiment is that you know where your source is exactly. You can measure the plasma with some also radiography and other methods. So you know basically the properties of the plasma and you can detect your proton beam at the end and measure the deflection. And in that setup, you can then compute diffusion coefficients. So just to show you the analogy, it's basically you shoot, that's the simulated plasma, you shoot cosmic rays through it and then simply observe the signatures of your proton beam.
How do you measure the magnetic field of the lab?
So there are certain methods where you shoot, for example, electrons or other charged particles through that, but not as a tiny beam, like a larger beam. And then at the end, you observe the pattern of that. And then you can, with some clever methods, deduce something like magnetic field strength and coherence length of it, just based on the pattern that you observe in the end.
If we can solve that inverse problem, why can't we do the same for cosmic rays?
Because here, I think you for sure know where the source is. So I guess in general, you just have less uncertainties.
It's not a Green's function.
Yeah.
Why is it interesting to do this? I mean, isn't the theory understood? Why do I need to measure it also?
Yeah, that's a good question. I mean, that's true, yeah. The theory is well developed for the high energy regime, but the goal is long-term to go to the low energy regime where you have not only small angle scattering, but then resonance scattering, and there are many uncertainties in the theory. So that's basically a first step to demonstrate, okay, we can do it at high energies, and at a future experiment, we want to aim to go to low energies. So as I understand, in these laboratory experiments, you first have to demonstrate that you can achieve something. And then after you have done that, the likelihood of getting time for another experiment increases if you want to have some more challenging. And yeah, this experiment that managed to describe the transport is shown here. So that's the signature at the end that you observe. Without a plasma, that's the inner circle. And then if you turn on the magnetized plasma, you see that the circle extended. And based on that signature, you can then deduce the root mean square velocity deflection and then the diffusion coefficients. So these are some simulations in the plasma, just to show you how the plasma in general evolves over time. And in the end, so that's the end configuration where you then shoot particles through it. It has a Kolmogorov spectrum with a limited inertial range. But when you compare the parameters and compute, for example, the ratio of your gyro radius over the outer scale of your turbulence, you see that it's much larger. Therefore, you are in the small angle scattering limit regime.
I understand that we're doing all this in test particle limit, so there's no back reaction on the field.
Yeah.
Is the field also effectively frozen in time?
Yes, yeah, exactly. Yeah, you can compare the time particles spent. So yeah, basically because so these particles are not relativistic, but you still can see when you compare the times. Not sure if you can see everything here, but yeah, they've done it. They compared the time they spent there with all relevant plasma effects. And also the density is low enough so that these few protons don't really mess up with the magnetic field over there. Their results that they published in the paper are shown here. So these markers, sorry for the mess in the plot, but I removed everything that's not really relevant. So the data points in the paper are here, and basically the x-axis is the path length, and that's limited by the plasma. So they only have a certain size of the plasma, therefore they can only probe a certain range of path lengths. And the different path lengths simply originate from the fact that they shoot particles at different times. So the plasma still evolves, and then the plasma had different sizes, and therefore they could observe trajectories after different path lengths. They computed the root mean deflection velocity and concluded that it follows the expectation that you can write down here. And that equation simply follows from small angle scattering in such a system. So the overall principle of that is like that. So you have your plasma, your proton beam, and then you have many smaller turbulence cells where your magnetic field is kind of correlated on a scale LB. And you have many of these, and on larger scales, they're uncorrelated. So locally, you have different magnetic fields, and your particles get deflected in each of these cells, correlated, because the magnetic field points in the same direction. So you can simply solve the equation of motion of a particle, which is simply delta V per. So it only depends on the Lorentz force, delta T times U per M. As a rough estimate, depends on the speed and the B field. And this one here, because you only consider in each deflection the time it spends in one of the cell, and dt times V is LB. And yeah, therefore you see basically that each initial deflection depends linearly on the size. Therefore you have also initially this linear increase, because yeah, that's the scale of the autoturbulent cell. So as long as you're within one cell, you have a linear increase of your deflection with respect to time. And when you go to the limit of many of these deflections, they should add as a random walk because they're unrelated. So the perpendicular velocity should scale as square root of n times delta V curve. And that's n is simply Li, if Li is the size of your plasma, divided by Lb. And if you insert that one here, you will see exactly that this equation turns out. So you nicely see these different regimes. Initially, you have a linear increase, then 1/1 square root of the path length. And at some point, your particles are isotropic, and then you can't increase your deflection velocity anymore at the end. And you can then convert that root mean square deflection into a diffusion coefficient using the scattering frequency and compute the diffusion coefficient then shown here. And exactly in that regime where you have exactly that behavior, where you randomly scatter over these different uncorrelated cells, you will get a converged diffusion coefficient. You can compare that one here, so this diffusion coefficient, with one that you would get by simply computing the spatial displacement of particles, which is the running diffusion coefficient that only converges once particles isotropizes. So this plot shows you that you have two different methods of computing diffusion coefficients, either by looking at the changes in velocity, and that works only until you isotropize particles, or you look at the spatial displacement of particles, and that works only after you isotropize particles. So these are two ways of computing your diffusion coefficient. And in the laboratory experiment, you can only use, because the size is so small, you can only use that one where you check how the deflection velocities change. So this kind of is the expected energy transport at high energies. So you have this e to the power of 2 behavior of small angle scattering. That's confirmed in laboratory experiments, but follows also a simple analytical theory and was well established already in many numerical simulations in the past. And you can still do interesting physics with that. So you can, at the highest energies, for example, try to understand signatures. So these are signatures of high energy cosmic rays. So you see some patterns. So they are not completely isotropized. You see some anisotropizations. And you can try to come up with a model of explaining, for example, your local sources, how they could contribute to such a signature that we observe. And one recent example or proposal of how to explain that was presented last year with the title Ultra High Energy Cosmic Ray Echoes from the Council of Giants, which is, so the basic idea is that you have one source that emits cosmic rays, which is Sen A, which is here. And then cosmic rays get emitted isotropically from there, expand everywhere. And these galaxies here, these are all magnetized. Here's our Milky Way. They will serve as kind of scatter centers for cosmic rays. So cosmic rays expand isotropically, and as soon as they get captured in these galaxies then have captured cosmic rays, and from these scattering centers, cosmic rays can then also evolve isotropically. So you expect in the end some echoes from that source, especially if there was an outburst in the past which emitted cosmic rays. They will be captured by these galaxies and then re-emitted towards the galaxy. And they run some Monte Carlo simulations and kind of showed that if cosmic rays, shown here in blue, get emitted here at some time in the past and evolve, at some point the echoes will all more or less simultaneously arrive on Earth. And even though we believe that individually these sources here in our local environment cannot contribute to the observed signature, it could be indeed that in the past the active source here emitted so many cosmic rays that are now seen as an echo from the surrounding galaxies. And for that method, you need some assumptions. One assumption is that the mean-free path of your cosmic rays in your center, in your galaxies, is comparable to the radius. So what they assume is your cosmic ray enters and isotropizes on a radius that's comparable, or on a length scale that's comparable to the radius of the galaxy. And once it isotropizes, cosmic rays basically diffuse radially out of it. And then you have a fraction of cosmic rays that also will find its way to the Milky Way. So that's their basic argument. So you have cosmic rays entering, isotropizing, diffusing, and then getting out.
But what would be the time scale for that?
That's a good question, and that brings me exactly to the quiz that I want to ask you. So consider two different cosmic rays in such a setup. One with high energy that basically enters the galaxy and only minorly deflects and gets out of it again. So that's case E. The other case of a low energy cosmic ray that enters this magnetized galaxy and then slowly diffuses and performs almost immediately a random walk. And the question is, what's your intuitive understanding? Which one will remain longer in such a setup? So if you think it's A, you can raise your hand. So the diffusion one. And that one. So both cosmic rays will enter. So let's call it EB and EA. And we have that EA is much smaller than EV. So that one will strongly diffuse, while that one will only experience small angle scattering and then will exit the galaxy at some point. And this one here will also enter the galaxy, but then strongly diffuse because of the low energy, and also exit at some point. So that's just an example trajectory, will exit, for example, here. And the question is, which particle remains longer in that galaxy?
Very much depends on in what direction it escapes or not.
And an average. So if you average over many particles, average over that.
A will get out quicker.
A will-
More space, the curvature of this. More likely to go out the way he came in.
That's reflected.
Exactly. That's the right intuitive understanding, but it turns out that the time is exactly or roughly the same. So in 1D you can see that rather easily because you can if you have a distance d, you have a cosmic ray with high energies, the time it spends is simply d over c. But when you have a small energy, your cosmic ray will isotropize on a mean free path lambda. And then from this lambda, it will have the same likelihood of turning left or right, but it needs much longer to get to the right. So the probability of escaping to the right, it's should be lambda over v. And the time it spends while escaping there is v minus lambda, because that's the distance over the diffusion coefficient. And you can do the same for the other fraction of particles, that is v minus lambda over v times lambda squared over kappa, plus your initial time you need for the particle to enter, which is lambda over c. And if you do the math, you will see that you get exactly that one. So in 1D independent and in a
So you're
paper,
saying the time will be the same?
on average, not for each individual one, but on average. Because the argument from Chris was exactly, if you enter, then it's most likely that if you have a small diffusion coefficient, that your particle will just
Yeah, but,
basically hit through.
sorry, but we are thinking this in the context of this observation, so I think not, so in the echo, we are, if you're, I am still thinking about this echo thing.
Yes.
So I asked for the scale because I think if you want some correlation in the signal, you need to understand how much time this will be inside each galaxy and then come at the
Exactly.
same time to see
Yeah.
some correlation, otherwise.
But that's exactly the answer. On average, particles remain the same time in these galaxies independent of the energy. So what really matters
Even
is,
when you're trying to observe them from a given direction. I mean,
yeah, so
if the
Yeah.
Milky Way is down.
that's true. There should be some bias, yeah. That's true. So it depends at the end. That's true. If you observe it like here on Earth, that's true. It takes longer for those particles to get deflected by that angle compared to if your Earth is here, because yeah, that should be faster. Yeah, there should be some time dependence. But it seems that roughly the geometry is such that the angles are roughly similar, so there aren't big differences
And-
between these
And I
galaxies.
had another question, which is there an effect when this cosmic ray enter our galaxy and then go with the magnet?
Yeah,
in
that's-
our galaxy?
Yes, yeah, it's the same. So low energy particles have a difficulty in entering our galaxy, and especially Earth, because Earth is not at the outer bound. So particles, most low energy particles just get deflected and never manage to get deep into our galaxy. High energy particles don't have any issues with that. Yeah, these are just some numerical simulations that I've then performed, and depending on the energy, you see that indeed, when you go to lower energies here on the right, so purple are all these lines that make it to our galaxy, that then there will be many kind of echo signals that we could kind of observe. Now I move on to the next points, and these are a little bit shorter, so I know that I can manage in time. When you go to the smaller scales, you will get some micro-instabilities, and one really relevant one is the mirror instability. So once you have large-scale structures that looks something like that. That came out of numerical simulations of different setups. You will see that the magnetic field decreases at certain parts, certain spaces, and increases at others. And that should trigger micro-instabilities. One dominant one is the micro-instability. When your particles then evolve microscopically following the turbulent motion of your plasma, you will have in such an environment pressure anisotropies simply by obeying these equations over here. So if you increase locally the magnetic field, you also increase perpendicular pressure. And at places where you already have kind of a strong pressure anisotropy, you will, or your particles will change the magnetic field strength. So here, if you blow out these magnetic field lines, you weaken your magnetic field here. So it's weaker compared to there, where it's much stronger. So you're effectively forming mirrors in your plasma. And that should trigger the, so these pressure anisotropies trigger the mirror instability that results in a strong small-scale fluctuations of your magnetic field. There's some evidence from observations of the solar wind. When you look at temperature anisotropies, you will find that indeed, so that's the mirror criterion, and that's the one for another plasma instability, kinetic instability. You see that both operate and prevent the plasma from getting to anything that's above these conditions. That's evidence for that these micro-instabilities work in the solar wind. And in particular, it should also work for all other high beta plasmas, in particular the ICM as well. There we don't have a nice proof, but we can numerical simulations. That's something Archie Bott and Matt Kunz have done to artificially increase the magnetic field and then trigger the mirror instability. And we will see that on small scales, there are these enhanced fluctuation centers where you have stronger magnetic field. And similar to the case that I've explained before, where you have these kind of uncorrelated centers that deflect particles, you would also expect that when a particle moves through a field such as that, it will get also randomly deflected, and that under certain assumptions should lead to diffusive behavior. And just for the scales, that effect happens on a really tiny scale, so that's the Larmor radius scale. If you want to express it here, it's a factor of 10 to the power of 12 to zoom in. So it's even smaller than anything else that they cared about in the simulation. So that's certainly, that effect is certainly not resolved in these simulations. The cosmic ray trajectory of low energetic particles then now compared to the high energy one is again, tiny if you really zoom in. For comparison, you see that the scales, you can compare the scales of these effects with something you know from our solar system. They're really tiny, but we argue that similar to the high energy regime, these fluctuations introduce small angle scattering. And with similar arguments than before, you end up with a scattering frequency that then depends strongly on the energy of your cosmic rays or the gyro radius. Here, gyro radius to the power of 2 and energy to the power of 2, and also depends on your fluctuation level. So delta BMM is the fluctuation strength of your micromirrors. And we've picked the micro-instability as the one that's most likely to influence cosmic rays, because this ratio is larger than for all the other instabilities that you are aware of, also the fire hose instability, for example. You can convert that into a diffusion coefficient that's relevant given certain conditions that you have in your environment. We run then numerical simulations, so test particle simulations in these simulated fields from the PIC simulations, and computed then diffusion coefficients now, and compared them with our theoretical prediction. And that's for parallel diffusion, that's for perpendicular diffusion, and it nicely matches. So you can now add these simulation results to this overall plot at low energies. At places where micro instabilities appear in the ICM, in particular the mirror instability, we expect small diffusion coefficients that follow this e to the power 2 dependency and are roughly at this place in this overall diffusion coefficient plot. There's one example that was recently published by Robbie 2 weeks ago, and I will cover that quickly tomorrow in the Astro Coffee, present that paper, so I don't spend time now on explaining that. But the rough idea is that you can use micromirrors that surround these radio bubbles as one potential mechanism of confining these cosmic rays to these radio bubbles. Another example that I just quickly mention is the Cygnus cocoon in our galaxy. So that's a star-forming region. There, observational evidence exists when you look at gamma ray observations from Fermi, but also LASSO and other telescopes, that especially at small energies, because I told you before that you have this connection between transport and how transport affects the spectral shape of your cosmic rays. And the spectral shape of photons closely relate to the spectral shapes of protons in that environment. So by observing gamma rays, you can infer the spectrum of protons. And you see that there's a cut, and at low energies, the spectrum is pretty flat. So it's close to the spectrum that you would just expect from acceleration at sources. So the idea is, or the possible explanation is either that there are strong winds that blow up particles, so particles don't have time to diffuse. Therefore, diffusion is not relevant, and the spectrum that you observe matches the one at the sources. The alternative is that you have tiny diffusion coefficients that could be provided by the small angle scattering by micromirrors, as we propose. The diffusion coefficients would be tiny, and particles would be simply not leaking out yet. So the picture would be in this leaky box picture. The cosmic rays started at the source, but diffuse so slowly that they do not manage to get out of the source. And if there isn't any leakage out of the system, then you don't change your spectrum. So that could be another potential idea. And there are other constraints at high energies that, I don't want to go into details now. And there's one regime remaining, and that's the most complicated one, where you have resonance scattering, and it's in general pretty difficult, and there were many different theories. Last week there was a nice workshop here in Princeton at ICTS, where there were some interesting talks about that regime, and there were some long-standing theory of UKP and others, quasi-linear theory scattering of waves that was believed by a large fraction of the community for a long time, but there is recent evidence that the dominant transport mechanism should be scattering of structures, some recent papers. But I think the overall relevant point out of all of these studies is that the energy dependence is of the diffusion coefficient shown here, something like 1/2 and 1/3. So independent of all of these different methods, the spectra that they assume for the turbulence, it turns out that the outcome is pretty robust and looks something like that in that regime. So you have either energy independent diffusion, which is rather unlikely, or something between e to the power 1/3 or 1/2. And the interesting point that I want to make here is that for diffusion coefficient, it always matters that you have to compare it to other things. And in particular, you have to compare the micromirror diffusion here that we propose with all the other effects that are potentially there. And only that diffusion process that has the lowest diffusion coefficient will dominate in the end. And so our picture is that below TeV energies at the ICM, so in galaxy clusters, micromirrors dominate the diffusive transport of cosmic rays. Above that, different resonance scattering mechanisms should set in. There's still lots of uncertainties. It would be really nice to go with laboratory experiments into that regime to test it. But at the moment, we only have convincing results at the highest energies, where already the theory was pretty clear and numerical simulations were clear. But I guess for the future, we managed to go at least a little bit in that regime. Maybe it's not sufficient to discriminate between different regimes, but I guess over the next couple of years, there will be some exciting news in that regime. And with that, I'd like to finish my talk.
I have a question. So the GeV energies, is there room for streaming instability, or does it have to be mirrors?
There could be a streaming instability indeed.
What would that be?
So whenever there are mirrors, it's unlikely that there is the streaming instability, but most likely the ICM won't be so there won't be everywhere micromirrors. So it's more likely that micromirrors will have a certain percentage of volume filling fraction, and there will be other areas like approximately on the order of 10% of the medium will be mirror unstable, and in the 90% of the remaining plasma, there would be most likely something like the streaming instability.
So I guess, how does this plot change if you go into the plane of the galaxy?
Then it will most likely be something more like, so that should be remain similar. I mean, the scales in the end change, because magnetic fields may change slightly, but in the end, you will have something like the streaming instability that would be more energy independent over here. So wherever you don't have micromirrors, you don't have that steep.
And the driving scale of the turbulence is not on this plot?
That's basically here. So the driving scale, so it's only I converted the gyro radius for that given energy in the ICM, and that corresponds to the driving scale.
In the galaxy, it would be like 200 G.
Yeah, it would be much more. Yeah, exactly. Shifted to the left then.
Thank you.
More questions?
So it's probably one question. So since we know that across all the energy scale, the transport is more like a diffusive process, and we can always use this random walk type of model. So does it mean that the only thing that matters is the amplitude and the relevant length scale of the fluctuation that we need to apply into this random walk model? So at small energy, then you discover is the micromirror sets the length scale, and in the middle range, people discover that because turbulence isotropic, so maybe the structure matters and the curvature is irrelevant. So does it mean that what matters is only the length scale that we need to use for that?
I think so, yeah. If you want to summarize it in one sentence, I think, yeah, the scales and the fluctuations matter the most. I mean, in the intermediate regime, it's a little bit more complicated because you have to check the statistics, the coarse-grained statistics of curvature and so on. But yeah, it's just another scale, yeah, I think. You just have to find the correct scales that are relevant for cosmic rays.
Then one last question. No, let's thank Patrick again.